Hello, my name's Jesus Rodriguez. I was the Capstone 2 lead for the Analyzing Biological Networks group for this semester. And today I'd like to go over the demo video explaining our task of for this semester, which was the task of implementing the InfoMap algorithm into the SciFinder. And so I would like to give a bit of background information, and like of the methodology used in order to kind of go about the InfoMap algorithm before we kind of go into some of the finer details that we'll explain later on. So essentially, the InfoMap algorithm seeks to minimize the cost function or the description length of any amount of partitions within a graph. So by partitions, we mean if a graph is 25 nodes, we would split it up into any given amount of partitions and look to see which one would return using the map equation, which is the equation that is used for the InfoMap algorithm, which we'll explain a bit later into the video. We use that equation to try to figure out which one returns the minimum or like minimizes the cost function, or like returns the minimum description length out of any of the other partitions within the graph. And so essentially, the description length is obtained by giving each node in a module a unique code word using Huffman coding, which is a data compression algorithm, and that's something else we will kind of explain more into detail later in the video. So these unique code words are determined depending on the frequencies at which a node is visited within a module. Notice I say module and not graph. You are determining the frequencies at which a node is visited, like within a module, since you are trying to partition the graph into different modules, trying to see which amount of partitions would return the minimum cost function. And how do we determine the visited or how many times a node is visited within a module? That would be like a task for a random walker, which essentially is kind of used to describe the path taken at random through a network. And what I mean by that is, imagine a random walker in a graph. There's a graph of 25 nodes, for an example. If you have a random walker starting at any of the given like nodes in a graph, say there are 4 nodes connected to that one node where the random walker is at. The random walker is essentially saying that there's a 25% chance to visit each of the nodes, or any of the nodes, I should say better. So to pick a random node to visit, and say that node it just visited is connected to like 10 other nodes, so now it's a 10% chance to visit any of those 10 other nodes. And you basically repeat the process, and this random walker is going to traverse the graph entirely randomly while accounting for the frequencies at which a node is visited. And that random walker will traverse a finite amount of times, depends on how much you want it to run. And that's basically what's determining the node's visit rate, and therefore its code word. Unique code words are not only given to the nodes within a module, it's also given to the node when the random walker exits or enters a given module. So if a random walker leaves module 1 and enters module 2, you can expect to see the code word for like the exit of module 1 and the code word for the entrance of module 2 being used. So you need to take that into account as well. And the map equation is primarily the formula used in the InfoMap, as explained before. This is what's going to calculate the per step description length of the random walker's movements. It's essentially going to say which is the smallest per step description length of the random walker's movements out of any of the given partitions, and return the smallest one. And it will say like this amount of partitionings will give you the smallest, or will give you the most optimal, path or condensation of the Huffman coding, or the code words for the nodes, depending on the partition. We'll explain the map equation a bit more into detail later on in the video as well. So the goal of the InfoMap algorithm, so as you could see in the image on the left, we can see that this image B is like all of the nodes are encapsulated into one module. This is all encompassing all the nodes as one module and treating it as such. You could say it's like the graph as a whole, and it's just treating the entire graph as just one module. And as on the bottom, as you can see by like the different bit code words on the bottom, that is just describing the path that the random walker took using the Huffman coding. And we can see that like adding up all the bits together, we get 314 bits. Or getting all the bits together and counting them up, we get 314 bits. Pretty long. When you compare it to image C, on the other hand, where you see like a red module, orange, green, blue module, these are like the nodes are now partitioned into 4 different modules. And the reason this is more optimal and returns a bit length of 243 bits as opposed to before, where it was 314 bits, is that when you're partitioning it, the nodes or the graph into different modules, you can afford to reuse Huffman code words within the graph as a whole, just not within the community. So to kind of give an example, if we look at the orange community in the top right, we see like the node to the most left is 111 in the orange community. And that's the only 111 code word in the orange community. But you can also see that right next to it, it's connected to another green node, which is also using the code word 111. But the reason this is allowed is because they're only using Huffman codes, unique Huffman codes within a module, which allows for reusing code words like throughout any of the other given modules, and is why like image B, where you're only showing the graph as one module and encompassing all the nodes into one module, is going to return a long bit length. It's because since you're keeping all of the code words in one module, all of the code words need to be unique, and since there's 25 unique code words, it's going to suffer the cost of having to be too long, essentially. And you're going to have to like make the code words longer in order to compensate for that. And something else to keep in mind for image C is that, just as stated before, there's the entrance and exit probabilities, or the entrance and exit code words that are needed to be used. So essentially what InfoMap is trying to do is it's trying to find a balance of trying to keep the nodes or the Huffman code words within each module like as short as possible, while also not trying to let the exit and exit code words for like each given module like too long, and trying to find a balance between the two. And as you can see, partitioning the network into 4 different modules compared to only having one module yields a result that minimizes the description length by 32%.
Hello, my name is Jose Carlos Luzbel. I am a Capstone 2 student that's worked on the Analyzing Biological Networks project, and my main contribution to this project was Huffman coding. So as stated previously, Huffman coding is a technique that compresses data without losing any of the data being compressed. In other words, it is a lossless data compression algorithm. In this project, Huffman coding is used to assign code words to nodes in a network based on how many times each node is visited by a random walker. So if you have a node that's node A on a network and it's visited 5 times, its frequency would be 5. And so the length of the code words generated by Huffman coding is dependent on the frequency of the nodes in the network. This approach to Huffman coding utilizes a priority set, which is similar to a priority cube, except it doesn't include any duplicates, as a min heap to build a Huffman tree data structure. And the way we do this is by extracting 2 Huffman nodes with the 2 smallest frequencies. We add those 2 minimum frequencies to generate a new internal node that has a frequency that is equal to the sum of the frequencies of the extracted nodes. This process is repeated until the size of the priority set, or the min heap, is 1, which means that the tree has been built with the final root node being generated. So now we're going to focus on building the Huffman tree. So the figure to the right shows a Huffman tree that has been built, and I'll explain more on it right now. So assume we have a min heap with nodes A, B, and C, and their frequencies are 5, 11, and 20 respectively, which means that node A was visited 5 times, node B was visited 11 times, and node C was visited 20 times with it through the path of a random walker. So since node A and B have the 2 minimum frequencies, we extract nodes A and B and create a new internal node by adding their frequencies. And we add this new internal node to the min heap. So as you can see in the figure, we extract nodes A and B, we add their frequencies, and we get a new node a new parent node that has the frequency 16, which is just the results of their 2 frequencies being added. So now the min heap only has the newly created internal node and node C. We extract the internal node, that was just recently created, and node C, and create a new internal node by adding the frequencies of the extracted node as previously mentioned. And now the main heap only has the newly created internal node with frequency 36, so 16 plus 20, 36, and thus we can stop and we have our final root node and have built the tree. Now, in order to generate the Huffman codes, what we do is we utilize a recursive method that traverses the tree that we just made. And each time we move to the left, we add a 0 to the code string. Every time we traverse to the right, we add a 1 to the code string. And this occurs until we reach a node in the tree that has no children, so we pretty much stop when we reach the bottom.
Hi, my name is Maria Hernandez. I'm a capstone 2 student, and I work in the analyzing biological networks. I'm gonna explain the map equation, that is the equation using this info map algorithm. The main purpose is to minimize the description length of a random walker's movement on a network, and this will tell us how efficient the code will be for a given position in our network. So this specifies how consistently we can describe the trajectory of this random walk. So it would take a network and a partition of the network's node into models as input and measure how well the partition captures the network's community structure. When the equation is used, we should get from our code, we partition the graph into a certain amount of models, the smaller bit length.
Hi, my name is Seon Cho, and I'll be explaining about the original form of the map equation. And so the outcome of the map equation is gives the average number of bits per step that it takes to describe an infinite random walk on a network partition according to model partition M. And we can divide it into two parts. One is the red and the other one is the blue. And for the red term, it gives the average number of bits necessary to describe movement between models, which multiply by per step probability and the entropy of movements between models. And for the blue terms, it gives the average number of bits necessary to describe movement within models, which is multiplied by fraction of within model movements and the entropy of movements within models. And for this, the image below, we can see the outcome from the map equation, which is adding up sums of the red term and blue term, which is the movement between models and movement within models.
For this general equation, for the map equation, we can find the rate at which a random walker exit and enter each model. So this can be found by depending on the frequency of a node entering a community. Also, we can use the probability that any node is visited in a model. This contains the rate at which a node is visited in a given model divided by the total frequency of the model. And also, we have the fraction of time the random walkers spend on each model. In our case, we use the undirected graph map equation that was better suited for our project, that we use the relative weight of a node, the relative weight of a model I, also the total relative weight of link between models and weight of link exiting model I. So what the relative weight refers to is the weight of the edges exiting a given node divided by 2 times the total graph weight. This also, here is a picture of how the output will look in the community one.
All right. So to show off like the demo of what we worked on as a group over the semester, and like the progress we made on the info map algorithm, we'd like to show off a lot of the progress that was done, at least in the back end of our of the SciFinder project, and try to demonstrate a lot of the groundwork we laid during our time working on the project. So if we were to run the code really quickly, for reference, really quickly, I would like to explain that to test this, we're using random, how do you say, test graphs provided to us in order to like make sure that like the results we want stay consistent between graphs. So right now we're testing one called clustermedium.txt, and that's like the test graph we are using. So we'd like to start off at the beginning. So this right here, this string of text here, this is describing the path that the random walker took throughout the graph. So as we can see, it started off at a node called ABCG2, and then it moved on to like another node ERBB2, and then like you can see that like, you know, it traveled back and forth between the nodes before it decided to make some like movement like outside of it. And essentially what's going on is that it's accounting for each of like the nodes that it travels through, like the random walker, of course. This isn't only important like visually like seeing this in terms of making sure that like it actually does travel the graph at random depending on the nodes that are connected to the given node that the random walker is at, but it's also very important for making sure that the frequencies at which a node is visited is accounted for, which is going to be used in the Huffman coding later on, as we can see here. So for example, we have this where it says size of priority set 13, which you can also describe as a min heap. Like, you know, size of priority set 13 here as well, size of priority set 3 here, size of priority set 33. And so what we did to get these is that basically what's going on is that we're using the Leuvian algorithm implemented by previous groups to kind of partition the graph into 4 different communities. And so the 4 different communities, as we can see, are defined as, you know, A, B, C, B1, E, R, B, B2, or like this one would contain MG, MT, or KRT8, just as an example. And so we use that to partition the community into 4 different modules, you can say. And depending on those modules, we then give Huffman codings to each of the different nodes within the module. And so we can see here that, you know, ABCB1 probably had a very high frequency or high visit rate because its node, Huffman node, is 0. It's very short. It's like only it's only using 1 bit to describe the path within the community. And so we're using all of these Huffman codings to kind of like define unique code words within a given module. And this would be very important later on when we would like to, for future groups at least, when we'd like to implement additional features that would have like, or print out the random walker, or like the description length as described previously within like, you know, like either like the console or, you know, like a text file or any of that. And essentially, to get to the very end, the average bit length of like the partitioning of this graph is calculated to be 2.45. And it goes on for a little bit longer, but 2.46, I guess you can round it up to, would be the result you get from this. And this is what we would describe as the per step description length that the random walker took previously in the video. So as we can see, this was something that was like able to be calculated using methods from this class right here. This has the methods to be used for the map equation, just the default general map equation that was explained previously, while also having functions for the undirected graphs. However, we felt it was more necessary to use undirected graphs, or the map equation formula for undirected graphs, given the fact that most, if not all, of the testing graphs that we have are undirected. So we use a lot of like the map equation for undirected functions, or like the functions for an undirected map equation, as seen here, to calculate the map equation, and that's how we came to this result right here. And this basically gives you like the per step description length of the random walker and like the steps it took throughout that graph. To test it out even further, we can use another graph. We can use the lungcancer.txt graph, which is actually the testing graph we use for most of our project. So if we were to run it, we could expect to see that the results are going to be like relatively the same. So like we can see like these are the steps that the random walker took. This is the different communities that were defined. As we can see, 4 communities were defined again, each giving them different Huffman coding values. And we can see that the average bit length of this partition is 3.978, which makes sense because you are looking at a graph with a much larger sample size, so the average description length of or like, well, the graph has many more nodes than the cluster medium text, so you're looking you're going to be looking at more the cost function is going to be a little bit bigger because you're having to use more bits to describe a unique code word, despite the fact that it's split up into different communities. But it still minimizes it to 3.97, and that would be like the result we get from running the Leuven algorithm and running the Leuven algorithm to partition the communities into different communities or modules, and running the map equation algorithm for undirected graphs on it. Well, there's a lot more we would have liked to have shown or have ready for this presentation. This will be something we'll explain further on in a later video where we explain our wish list and our shortcomings. But that will be all that we have to demo for right now. And yeah, we'll see you guys later.